Yeah, I know. Big improvements.
Yeah, no worries.
Good luck. You got this.
Just cover the. That's on your screen. Well, I'm not. You make us look good. Sure. Oh, yeah.
Okay, so we'll go ahead and get started then. Real quick, what I wanted to do is do some professor introductions. So if the professors here could go ahead and introduce themselves real quick.
Okay, my name is Serdar Erbatur. I'm a assistant professor of instruction. I teach algorithms, discrete math, and I have theoretical plus some practical interests. My research field is theorem proving, which is a subfield of AI in general. So I'm happy to be here tonight and like chit-chat afterwards. Thanks.
Okay, so I'm Gopal Gupta, professor of computer science, and I teach computational logic and research in automated reasoning, explainable AI. So if anybody is interested in that kind of research, I have some people here who can research it.
I'm Doug DeGroat. I currently teaching digital logic and professional responsibilities in computer science, which is a hard thing to figure out. But I led AI Symbolic Computer Group in AI at Thomas J. Watson, and I was the head of the Symbolic Processor Group at Texas Instruments. And I joined, and Gopal and I have a long common history in logic programming and AI systems. So I'm happy to be here at UTD for the last 3 years and working with Lakshman and Gopal in our Center for Applied AI and Machine Learning. So it's nice to be here with you all tonight.
Well, I'm very pleased to be here. Glad to see a lot of you are interested in AI. I am Professor Lakshman Tamal. I am a professor of electrical and computer engineering. I work in the area of AI related to healthcare. So I'll be happy to help you all in the area that I can do. And I'm looking forward to seeing your presentations.
Okay, so welcome everybody to AIM final presentation night. My name is Omar. I'm the AIM program director. Thank you for coming. Again, we haven't gotten a chance to do really any AIM events in person, so I'm glad that we get to do this one here. I don't want to talk for too long because, again, the point of tonight is for the mentees and their presentation. So real quick, let's go through a little bit of background about AIM. So AIM, or the AI Mentorship Program, was launched by AI Society here at UTD in spring 2021. So this is our second semester of AIM. We made an effort to help people learn about AI and machine learning, make it more accessible. As you guys have probably seen, AI and machine learning is something like pervasive in almost all parts of computer science now. So it can be a bit daunting for somebody to try and get into the field on their own. So we begin with grouping together mentees and mentors, and we have about 5 weeks of learning about machine learning, and we have a focus on neural networks and types of neural networks. The second half of the program consists of mentees building a project of their choice, and then they'll demonstrate what they've learned tonight, hopefully. So to go through the schedule for tonight, again, the mentees have been working on an ML project for the past few weeks. They're going to present their projects. We'll try and wrap up around 9 p.m. So we have 12-minute presentations per group. So there'll be a presentation and then a quick demo of the project. And then afterwards, after each presentation, you guys will provide feedback to the mentees. And yeah, so we'll have like a timer. I'll let you guys know when your time is up. And yeah, so if there aren't any questions, we can get started with the projects. Okay, cool. So the way
Can you check that microphone to make sure that's on?
there's no mic.
That's something. Yeah, there is.
I mean, draw it closer to you.
It's on.
You hear me now?
You can just go around the.
There you go. Yeah, start speaking again.
Hello?
Okay, stand up, look in front of them, down.
Can you hear me now?
Say something, talk
Hello?
about like
Hello?
AI. AI is
Hello?
great.
AI is amazing.
Perfect. Yeah, we want to push this. We're just gonna have the speakers to talk a little bit louder. Yeah.
All right, so the way that we're gonna do this is we'll have each team come up and then they'll share their screen. So there won't be a need for like an HDMI cable. So you guys will do your presentation and your demo by sharing your screen. So if team 1 can come up and present their project.
How many teams do you have?
6.
So you took 10 weeks to make this?
5.
5. Now it says week 10.
Yeah, so 5 weeks was for like teaching basics of AI, and then the last 5 for like building the product.
Oh.
You won't need to if you're sharing your screen.
Speak loud into the mic. Okay.
All right, well, we got it set up. I get a little speech about AIS itself. So the AIM program here, it's called the AI Mentorship Program, and it's being underneath our organization called AIS, the Artificial Intelligence Society. So we're one of the largest student CS organizations here on campus. So if you come to any of our events, you probably know like most of the stuff is pretty diverse what we do, which such as like NLP, ML, deep learning, reinforcement learning. We did a lot of workshops and collabs in the past, and so we're planning to do more. For example, we're having our hackathon, annual hackathon at Hack AI next semester. So if you guys are interested in that kind of stuff and really like trying to learn this field, it's part of it's supposed to be intimidating, and that's the fun part about it, trying to learn something new. So if you guys really want to break into it, this is a really perfect opportunity to hear, learn tonight, and for future events at AI. So I'm going to let the first group go ahead and get started.
So if I can add one more thing, and that is last year we had this hackathon called Hack Reason. So January 14th is the World Logic Day. So it was declared about 2 years ago by United Nations, January 14th to be the World Logic Day. So last year we organized Hack Reason Hackathon in fact, the AI Society was the one that organized it. We did, wonderful job. So we'll have it again, January 14th, we'll have Hack Reason. There are prizes of about $1,500 or $1,700, something like that. And so it's about automated reasoning. So you have to go through a couple of workshops and then you can participate. So I hope you will join for Hack Reason as well on January 14th. So you can mark it on your calendar. It has to be on that day because that's the World Logic Day.
It's an amazing hackathon. I really appreciate Dr. Gupta for talking about that. Y'all should all do it. We'll be seeing your faces virtually. Everybody better be there.
And it's online, yes, it's all
Yes,
online.
it's all online. You
Yes,
can't,
and there'll be
can't.
lots of mentors and other people who will be helping you, so, that's a good way to learn automated reasoning.
It's the best. Not
January
because I do
14th.
research.
Gosh, I wish I had a movie to watch, but I just don't know what's interesting to me anymore.
Yeah, I don't have the energy to spend hours scrolling through Netflix and just find what movie I want.
Hey guys, why don't you check out our movie recommendation system, presented by Hemel, Solman, and Yusuf. So a common activity people do in their free time is watch movies. But what if you can't find the right movie to fit your preference? That's why we built the movie recommendation system. This project is split into two models, one that incorporates sentiment analysis and one that classifies movie genres. First, the system will ask the user a set of questions asking what type of movie they want to watch. And according to the input, it will generate a list of movies that align with the genres that the user wants to watch and along with movies with high reviews.
Here's a really short demo. So just like Himmel said, we want to have some really user-friendly questions that a user can answer without knowing what mood they're in. And so, like, you have a lighthearted movie. As you can see, I'm really indecisive here still. But these questions are supposed to be really easy to answer, and once you answer them, the model can determine what genre you're in the mood for, and it will recommend the movies for you. For example, here I answered yes to lighthearted movie, and I answered no to the others, but yes to a movie that's going to make you laugh. And so the quiz determined that I want a comedy movie. And so it here outputs the top 10 comedy movies. And this, the first line is associated with that line down there, and it shows the comedy score of the movie that the model determined. And at the very bottom is the sentiment score of that same movie. So to design this model, we used two similar data sets to train each model. We used the Keras IMDb dataset to train the first model for the ratings through the critics' consensus, and we used the Kaggle IMDb dataset to train the second model for the genres through just the movie descriptions. And then we used the same Rotten Tomato dataset to get models to be able to make their predictions. And we then used the user quiz to determine what genre the user wanted. And based on that, we outputted the movies of those predictions and just the top 10 movies of that genre. And we used Keras and Tensorflow to build our models. A lot of our calculations were performed using NumPy, and we used NLTK to tokenize our words in both models.
So as an overview for Model 1, we trained this model on the Keras IMDb dataset, and this dataset was already pre-processed. So this dataset had a list of critics' consensus movie reviews, and the dataset classifies these movie reviews on a scale of 1 to 0. So it will give a score of 1 if it's positive and 0 if it's negative. And in this model, I built an Lstm network. And so this network allows the model to learn how to classify which type of reviews. And in this model, it will output, again, the same range of 0 to 1. So after the model is trained on the Rotten Tomatoes dataset, it will output a value closer to 1 if the review is positive, or a value closer to 0 if it's negative. And within this model, we used binary cross entropy, the atom optimizer. We used 15 epochs and a batch size of 100. And we have 3 layers within this model: the embedding layer, which converts the words into vectors with the same size. And the Lstm layer is essentially the network, which allows the model to train using sentiment analysis and retain this information. And it incorporates the sigmoid and tanh activation functions. And then we have the dense layer, which transfers the information from the previous neurons to the next neurons. And for the analysis of Model 1, the model performed relatively well. It had an accuracy score of around 0.86. With this accuracy, some results were slightly off. And to add some improvements to the model, we could incorporate more data. So when the model trains on more data, it's exposed to greater variations of critics' reviews. So it has, by being exposed to more variation, it'll be able to make more accurate predictions. And we can also change the batch size or the number of epochs to see if different values allow it to be more effective.
So I worked on the second model, which essentially takes movie descriptions and labels genres for that movie. And so what I used was the IMDb and Rotten Tomato data set from Kaggle, and these weren't pre-processed. So I essentially had normalized the text by removing stop words such as A and the R, lowercasing words, and removing special characters using the NLTK library. And so from there, as you can see in the image below, I just added columns for every genre that showed up in that data set and flagged it 1 for yes and 0 for no if that movie fell into that genre. And so once then from there, the descriptions were tokenized, turned into series, and then added using Keras. And we use Atom as an optimizer, binary cross entropy, and a batch size of 128 with 15 epochs. And so the first layer is a embedding layer, which essentially turns text data into numerical data and then serves as input to our model. And then from there, there's a Lstm layer. And what the Lstm layer does is, because we're using text data, it's better to use a sequence of data rather than a single data point because the context and the words around a single word helps get a better value for that word. And so retaining the previous context was going to be important for this model. And then additionally, we used a bi-directional Lstm. This works just like the Lstm, except it goes both ways. So while Lstm may look in the previous direction, the left context, the bi-directional Lstm will also look more forward, so the right context, and this helps us get a larger context and preserve information from the past and future. And then finally, there was a dropout layer, which helps reduce an overfitting in our model and generalize model performance by switching off some of the neurons, which helps others work harder. And finally, we had a dense layer, which fed the output from the previous layer to all other neurons. So with this model, it's really small, but as you see in the image above, it ended up with an average accuracy of around 60%, and consistently the loss was reduced over time. And so some things we think that we could do to improve the model is bring up that accuracy to around 80% and use more bi-directional layers and units, and maybe train with more epochs while also not overfitting and just having more time to train, because one of the biggest things was waiting a long time for this model to train.
I was behind the user quiz, so for this I decided that I wanted to have parallel arrays for the genres of the movies and the scores for each genre, because I was going to determine whichever movie had the highest score at the end, whichever genre had the highest score at the end, be the one that the user most likely wants. And so for the questions, I decided to make an array with nested tuples in it, where each question is assigned a series of genres that are associated with it and their weights. For example, if someone wants a lighthearted movie, it's likely a comedy movie and romance and a family movie, and it could be a fantasy movie, etc. And then if the user answers yes to the question, then the scores list is incremented with the respective weight of the genre for that question. And the highest score is then marked, and that genre is recommended to the user, as you can see here in the demo before. Some challenges we came across in this project were finding the right data sets in our solution. At first, we were considering web scraping, and we had actually started before we found some data sets because we wanted to, we were just having trouble finding the right data sets. And in the data sets we found, there were still thousands of rows with invalid values, so we had to spend a lot of time cleaning that data. We also didn't have enough time as we would have liked to train our models, but that is an improvement for later. And some improvements we want to make for our model in terms of accuracy is, like we said, to increase the accuracy of model 2. And to do this, we'll probably try to utilize more data. We might use a few more bi-directional LSTMs. We're also thinking of using different sequence sizes for the LSTMs, and just having more time to train the same model, even without that many changes, would lead to improvements in its accuracy. We also wanted to make this project into an application eventually, to make it more accessible worldwide, and we wanted to have a feature where we would be able to tell the user what platform the movie is on that is recommended, just so they don't need to search between platforms. And in terms of user experience, we wanted to be able to ask fewer questions with better results to be able to determine the genre the user would like. And we wanted to be able to implement a feature where the model can recommend a movie of multiple genres, such as a rom-com movie, for example. We don't want to just recommend a comedy movie. We want to also see the weight of the other genres. And we also wanted to later on implement a way to sort the movies based on the rating, so that the highest rated movies of that genre would also be displayed first. And that will all be in good time. So, thank you.
Okay, if y'all have any feedback.
So this question, you're predicting the genre, not the movie. You're recommending a genre, not a specific movie, right?
No, we determine the genre that the user wants through a quiz, and then we refer to our models that determine the genres of the movies, and we try to get the best movies of that specific genre that the user wants.
And in the end, you will recommend a movie.
Yes.
Okay.
So if the
So
user...
but you're using machine learning to predict the genre.
Yes, two models. One of them predicts the genre, and the other just predicts the score of the movie, just like Rotten Tomatoes. Yeah.
How did you judge accuracy? Was that based, how close you got to the IMDb score, or what? You were on the end, sorry, you were,
I think it will be good if you go back to the feature development slide there. Yeah, from there.
you think I can read that small?
So what, I mean, to reframe, so accuracy, I guess you had test data on which you measured it, right? So how do you decide on
What, yeah,
what's your training data, what's your testing data?
So
what is accuracy?
Yes, our training data was, let's say for model 1, since that was the accuracy, it was much harder to determine the accuracy of the genres neural network, just because no movie has a rating of how specific or how comedy is this movie, you know? It just gives the movie specific tags. And so it was much harder to determine the accuracy of that one. But in terms of the ratings, we just use the Keras IMDb dataset, and we use the critics' consensus to determine that, and the Rotten Tomatoes score. And that's how we determined the accuracy of the first model. The second model was a lot more complicated.
How big is your training data set?
In terms of
55,000.
You got it from Kaggle, right?
Yeah, Kaggle.
yes.
How many questions you have?
So far, we have 6 or 5 questions. It's just, do you want a lighthearted movie that's going to get you thinking, or scare you, or make you laugh, or an action packed? Yes.
But you said that you would like to ask, or in the more improved version, you would like to ask fewer questions. This is already a few, in my opinion.
Yeah.
So how much do you want to reduce?
Well, we're not completely sure, but all I know is to make it more, it's definitely not as accurate as it could be right now. And so the goal is to be able to ask it at least more accurate questions so that we don't need to increase the number of questions that we ask it drastically. So to change my words, I don't specifically mean decrease the number of questions. I just mean make sure not to increase, because the accuracy of this isn't as high as we would like. And to make it more accurate, we'd probably have to add more questions. So I want to try to.
This relates to the, Model 2 has 60% of accuracy. So
Yes.
this is about improving the accuracy of Model 2.
Yes, and this specifically is about improving the accuracy of the quiz. Yes, because the quiz then determines, like if the user wants a comedy movie, for example, so it goes to the new data frame we have that was created from the Model 2 that has all the comedy movies, and then we read from those and get the best outcomes.
So if you have a few more minutes, what about what is the exact, if you have, let's say, you want to go further and they want to improve the accuracy of Model 2. So what is the game plan for that? Do you have a plan already in your mind, or just within the next year?
So just some basic things we would do is we would keep trying to train the existing model we have and see if the accuracy just improves from there. And we would just get more data, maybe try a different data set. And if not, then I believe Salman said he would like to add some more bi-directional Lstm layers, as he has a hunch it might improve the accuracy.
Why do you think that your data set is not good enough? Is it overfitting?
I don't believe it's overfitting. Just as the problem is it's a multi-label. The model is a multi-label classification
only 5
model.
questions.
Oh, that is just simply for the quiz. For the model, it reads the movie descriptions of the data set and uses those to determine the genres that the movie is in. And so it gives each movie a percentage score based on the genre. And so
that's the one that has 60% accuracy.
Yes.
From natural language description of the movie to the genre.
Yes. And so what we did is we had 12 genres, so we used an epoch for each genre, and we did bi-directional, or we did a binary cross entropy for each run to try to be able to determine, because we were trying to do it using categorical cross entropy first, but it wasn't working just because this is a multi-label thing, and it can be multiple genres at the same time. Usually in categorical cross entropy, it can only be one thing at a time. So,
and then the training set came from where again for this one? Model 2?
The training set came from a Kaggle IMDb data set.
There is a training.
Yes.
The data set that maps movies descriptions to genre.
Yes.
I think we should probably out of time.
Okay. Okay, so we're going to go ahead with team 2.
That's why they say
Yeah.
They're asking good questions. There's no reason that. If I have a question, I'll answer that.
Or we just want to grill them for fun.
Hi, hello. My name is Nayeon Kim, and I developed the AI model for emotion recognition for texting dialogue with my mentor dog. Okay, let's start. This is the agenda for my presentation. I will test it quickly. So first, motivation. What makes me develop this model? Because of COVID-19, the world people suffered a hard time, right? We couldn't go outside and couldn't play with friends. So the COVID-19 changed the entire of our life. The global recession has skyrocketed, and also our family and friends passed away a year ago. Thus, naturally, the mental health of people also deteriorated rapidly. Look at these statistics. Oh, sorry. So look at these statistics. Pandemic causes spike in anxiety and depression. The symptoms of anxiety disorder and the symptoms of depressive disorder in 2020 have risen by more than 20% compared to the first half of 2019. This statistic is based on self-reported symptoms of US adults. If we extended this to all of the world population, we can predict that it could rise even further. This is the reason why I make this model. I wanted to develop a service that helps people's mental health. So how can I help many people's mental health? Here is my solution. I devised the model that analyzes a user's texting dialogue, such as iMessage, WhatsApp, and Discord. Based on these dialogues, it can analyze the user's emotions. For example, look at this dialogue here. So, hey, I ruined my exam today. And why does the professor keep giving me homework? This semester is so hard. Yeah, I think this user is very upset right now. As we have seen, we can feel a person's emotion in a conversation. And NLP allows machines to recognize human emotion. At this project, I used BERT, one of the NLP models, to recognize human emotions. I'll explain this in more detail in the next slide. Anyway, to summarize from the AI model's perspective, the input data is the multiple lines of dialogue. When this input is provided to AI model, it concatenates all sentences in the same dialogue and utilizes the BERT tokenizer to process the text. Then the output is a series of tokens starting with CLS like this format. First, in token embedding, two special tokens, CLS and SCP, are used to distinguish sentences. CLS is inserted at the start of the sentence, and the very first token in every sentence. And next, SEP is inserted at the end of each sentence. So it is used to distinguish the front and back sentences more easily. Finally, through the BERT model, we can get the data of the user's 7 emotions as output. Then what is BERT? BERT is the state-of-the-art NLP model based on transformer architecture. BERT can pre-train on large-scale dataset. So we can easily fine-tune for other tasks. That's why I use BERT for emotion recognition. Originally, the input to BERT contains embedding of tokens, sentence, and position of tokens. But at this time, we simply provided BERT with token embedding only for fine-tuning. So next, I use multi-modal emotion lines dataset, aka MEL dataset, to fine-tune for emotion recognition. MEL has been created by enhancing and extending emotion line dataset. MEL has more than 1,400 dialogues and 13,000 utterances from Friends TV series. Multiple speakers participate in these dialogues. Each utterance in a dialogue has been labeled by any of these 7 emotions: anger, disgust, sadness, joy, neutral, surprise, and fear. What we need to focus on this data set are the dialogues, utterances, and speakers. Based on the MEL train set data, this data consists of an average of 8 utterances and a maximum of 69 utterances length and a total 9,989 utterances. Also, there are 1,038 dialogues and 260 speakers. Why should we focus on this data is that our AI model analyzes the user's emotion by grouping the MEL dataset with dialogue and speaker. Look at this example dialogue. This dialogue input consists of 8 sentences, and the speakers are Joel and Chandler. The AI model analyzes the main emotion by grouping sentences by speaker. In this dialogue, Joel's main emotion are 50% neutral and 25% surprise and 25% anger. And Chandler's main emotion would be 25% each for joy, neutral, surprise, and sadness. Okay, let's go to the live demo part. I will show you real short live demo by using Collab. Here is the dialogue that I showed already in the previous slide. At this part, I tokenizes this text. And next, at this part, I concatenated text into this format. It's already told you previous slide. And then at this part, I made prediction. And the last part, I selected the emotion with the highest probability. So my output is disgust. So go back to my presentation. Next is lesson part. Actually, it's my first semester in US, and also it's my first time for studying AI and deep modeling. But our weekly sessions help me to understand better about AI. Thanks to AIS and AIM program, I learned transformers architectures for sentiment analysis and emotion recognition tasks. And I perform end-to-end AI projects from data processing to final classification. Lastly, my future development is that, add backend and frontend service to my AI model and run real service to users. So now, my AI model gets the emotion data of user. Then based on this data, backend service can generate users' mental health reports on a daily basis. For example, the app can show today's my emotion, the reason why I feel sad, if the reason is mentioned in the dialogue, and my emotional stats. Based on this report, the app can recommend various contents, such as music and funny YouTube videos to make users feel better. And also, if the user is at risk with a mental illness, it can also automatically send the user's emotion report to the hospital for treatment. So my presentation is ended. Do you have any question about this?
So when people write text, then they will use all kinds of abbreviations and they will not write normal English, right?
Yeah. Oh, yeah. Right.
So did you consider that, or you assume that the text that is written is all proper English with proper grammar and things like that?
Actually, at this time, I consider only English. But yeah, this is really nice feedback. So next time I will improve more about this.
Okay, so for example, instead of writing Y-O-U-R, people write U-R, right? Or
Yes.
to write Y-O-U, they will write U. And that's one of the challenges when try to analyze text or tweets and things like that. Because, good.
Also, LOL, they write love for love. Yeah, they say LOL. And emojis they use.
Oh, yeah.
But now, you say that you learn a transformer, right?
Yeah.
One of the characteristics of the transformer is it's overfits all the time.
Mm-hmm.
So did you test that your system is not overfit?
Can you repeat that question, sir?
Overfitting. Transformers are known for overfitting. That is a problem with the transformers.
Oh, yes, we did test. So the test set at pretty much bad. Like on a training set, we observed like the F1 score is around to be honest, 55%, which is comparable to a paper that we based on to build this project. And when we perform on the test set, and we just got about actually 22% only. So we did observe the overfitting picture.
So what's the F1 score you got?
So F1 score, for training, we got 50,
How much?
55.
55.
Well, on the test side, we just got 22.
What about the accuracy and things like that?
But accuracy, we saw 60.
60. So it's on the low side, you would say, right?
Yes. To be honest, here we use a distributed model, but on the model that the paper we based on, they use the Roboter model. So actually, we didn't try the Roboter, but we just probably solely focused on the group and distribute.
Also, okay, the training data was the conversations, dialogues from friends script, right?
Yes, right.
So are there any other sources like it? For instance, what happens if you try, say, How I Met Your Mother? Or something close to still comedy, but a little bit darker. Like if you train a model like this or a tool like this on other sources of data, like training data, do you think the performance will change? What would happen? How would your outcome or the performance of your tool change? What do you think? Or is it meaningful at all?
So you said.
What I mean is, okay, I think the training was done on the dialogues from the script of, let's say, France.
Yes.
What if we change, instead of France, let's say we have some dialogues from another TV series or another culture item. So let's say, How I Met Your Mother, or something a little bit darker, but you use dialogues from it. And what would happen to the performance of it? Like, I think if there is another training data, set of training data, you must try that too.
I think the performance would get worse there because basically the data set here we use is kind of small. Number of utterances is only about like 40,000. So definitely that when we try with like different dialogues from different TV series, probably I think the performance will get worse. Yeah.
You mean it will change? Or
Yes, it will change and get worse. I believe so.
What's your data set? How big is your data set?
Can you go back to the slide?
1400 dialogues, right?
I think number of utterances is 14.
But you have the pre-trained BERT model together with it, right?
Yes, right.
So if you did not use BERT and just, I guess 1400 is too small.
So then the exact number utterances is 14,000.
How much?
14,000.
14,000. But if you did not use BERT, you just trained on the 14,000 data set. Did you try that? Did you get any?
We didn't try it.
Because sometimes BERT helps, sometimes it doesn't.
Okay. All right, thanks.
Just be yourself. Because another one from I think I have to credit so. I'm not sure. I think so. I should be asked. How did you research it? I don't know. And just do this.
6.
This guy. And do yeah. I mean, it's 12, that's 12, but like, yeah, no,
Hello, everyone. My name is An. I'm from Team 2, and today I'm very excited to present my whole semester project by Ai Mentorship Program. So I'm working on this project with my professor, Ovidio Dasku, and my mentor, Damo. So during my time in AIM, I worked on developing a software package to find within the last 10 years how many deep learning medical publications in top CS conference have moved into clinical trial. So to be more specific, my project is to conduct varied natural language processing techniques for web searching and online datasets, producing a software package that can be downloaded and applied anytime. So the motivation of this project comes from the fact that deep learning application has been really significant in medical field. Deep learning in healthcare can uncover a lot of secret and hidden opportunity for doctors to help giving patient a better ways to cure some serious diseases. So for example, during the pandemic, there's a lot of deep learning research on COVID-19 lung detection using ultrasound imagery. Because of that and the fact that it is really hard to find a tool to search for relevant publication, a search engine for deep learning-based medical publication is really necessary. And researcher and AI enthusiasts are gonna find it's really helpful to have a tool that can filter out and narrow down the result out of 1,000 of public medication publication. The software package also works on online dataset and can be applied and download anytime. Moreover, another motivation for this project is because I have a personal interest in natural language processing, which is the ability of AI to conduct which is the ability of AI to understand language by context. So by using NLP, we can better extract data or information from text-based documents and improve on more complex analysis tasks. So here are other steps or roadmap that I took for my project. So first of all, I conduct web crawling for all the articles that are relevant to deep learning and medical publication. In clinical trial from online resources, I found those resources mostly from AI conferences such as AAI, NeurIPS, ACL, CVPR, or medical conferences such as Nature or PubMed. Next step, after getting data from those resources, I start pre-processing them to get them ready for the next task. After that, I retrieve article based on TF-IDF scores and then apply Cyber to find the top relevant articles. After getting result from Cyber, I conduct ranking for the best candidates and then finally display the result on user terminal. For the next slide, I will walk through each step in details. So this slide have a table that show example of resources I used to crawl the article and number of articles that I pulled from them. I crawl the article using Scrapey Python package, and I retrieve article by passing the URL of the pages in the correct format to some function from Scrapey. So from PubMed, I'm able to pull around 32,000 articles, and from clinical trial of government, I am able to extract 4,500 articles. So article data crawl from resources then are stored in CSV5 and then ready for the pre-processing task. So I pick out the corresponding columns that containing text data for titles and contents of the article to start cleaning them. So I clean it by creating a function that separated titles and content, then removing unwanted characters, trailing or leading spaces, URLs, hashtag, or extra new lines. Data is then stored in a text file ready for TF-IDF algorithm. So what is TF-IDF that I've been talking about? TF-IDF stands for term frequency inverse data frequencies. Term frequency, or TF, give us the frequency of the word in each document in the corpus. It increases as the number of occurrence of that word within the document increases. Inverse data frequency, which is IDF, used to calculate the weight of rare word across all documents in the corpus. The corpus that occur rarely in the corpus have a high IDF score. So combining those two, we come up with TF-IDF score for a word in the document in the corpus, which is the product of TF and IDF. So why do we need TF-IDF and how do we use it? So TF-IDF is a measure which is used in the fields of information retrieval and machine learning that can quantify the importance or relevance of string representation in a document amongst a collection of documents. Computing TF-IDF will help retrieve the most relevant article given query among all the potential results and candidates. And I use TF-IDF to compute the score for the titles only. And the reason is gonna be explained in the next slide.
So only the score of the paper title?
The titles, yes. Okay. So here's the more detailed step or the overall step that it used. So given a query, for example, COVID-19 lung detection, I will perform data preprocessing as mentioned above, which is cleaning and then compressed in a text file, and then computing TF-IDF score for each document given query. After that, I'm going to select top 1,000 article with highest score, and then from there we can save the article TF-IDF score into cache to display more details than requested. So the next step is using Cybert, which is a pre-trained BERT-based language model for performing scientific tasks in the field of natural language processing. It results in state-of-the-art performance on a wide range of scientific domain NLP tasks. And it's for the reason why I switched to Cybert, or I asked Cybert to the part of the task that I need to do for my project, is because for TF-IDF, the advantage is that it's really fast to retrieve regular documents, but it's disregard content of articles and not directly relevant to the query. But for Cybert, the advantage is that it retrieves article by content, but then it's slow and heavily computing consuming. When we went to Cybert, we want to take advantage of article abstracts for more relevant retrieval. Cybert is pre-trained on scientific publication across various domains. That is why it is able to extract scientific context from articles. So here is how Cybert actually worked or used in my project. First, given a query, data are going to be pre-processed by Cybert tokenizer and going to compute a query token. But but TF-IDF can do the same thing. But the advantage of Cybert is that it can work on contextual data. So given an abstract of article, Cybert can still process the text into tokenizer and output abstract tokens. We then concatenate query tokens, which are title, and abstract, which are contents of the article, then output this probability between 0 and 1. For 0, the most relevant article going to output the probability that near to 1, and 0 is the least relevant articles. So after that, we're going to take the result into ranking with perform descendingly, and then display top 20, but then we can still display more if requested. So for future development, this is a research project from a class, and I work with my professor, so it's a really huge topic to be done in within 5 weeks. That's why I would want to I want to still work on more on it and then produce a more potential result. And I want to make a more user-friendly package that can easily apply and then download, and also make a live demo. In the long term, I would like to add more personality to the package and optimize potential. That's the end of my presentation. Thank you so much for listening.
What you said at the beginning about one of your original goals? It was to find out how many of the scientific papers had published results on clinical, how many have moved into clinical trials?
Yes, so the
do
goal.
you get any data on that?
Yes, sorry. Thank you for the question. So the goal of my project is to to make a search engine that when user type in a query, like a keyword, for example, like retinal disease, then the package gonna return articles that are already public, but then in clinical trial level, which it apply in already in clinical trial.
So then are you trying to determine in PubMed or that, so you said top CS conferences, so these papers, if they're listed there, then you will look only for CS conference papers or?
Yes, so the project is narrowed down for CS related medical publication only, because we don't want to make the go too broad.
Okay, so then you kind of took all the papers in PubMed and narrowed down only those that were published in computer science conferences.
Yes.
Okay, and then in that set of papers, you look for whether there is a trial going on or not, whether they talk about a trial. Okay.
How did you determine that?
So first of all, there will be 2 times of scraping, which is, the first one is gonna scrape from PubMed, like medical conferences. Then those articles, those results that I took, I will apply another keyword or query for clinicaltrial.gov and then filter out from there, because in clinicaltrial.gov website, these are the publications that already got applied into clinical trial.
So you will try to correlate that paper whether there is a corresponding clinical trial.gov entry or not somehow. Okay. Okay. And what were the results? I mean,
the result is because I did not finish my project,
okay,
so I can't have a demo for to demonstrate yet.
So did you think about, using non-machine learning techniques? I mean, just basically string matching and those kind of things, because you're narrowing down your set to 40. How many articles did you get, right?
Like
42,000 or something.
Yeah, 32,000.
32,000,
yeah.
and then so the authors in the clinical study and in the paper are going to be the same, but could you is that the case? If you look at the clinical.gov entry and the paper, are the authors going to be the same, or there's an overlap or something? Could you use that instead of using machine learning? Use direct techniques. Was that possible? So a non-machine learning based solution will do only processing, just checking that a paper's author, do they have any clinical study registered under their name, for example, and then say, oh, I found 5 of them. Let's see which one corresponds to this paper, if there is any.
So like that's also part of the plan for future development, because for now I only have applied NLP to my project, and for future development I haven't got to that point yet.
May I answer that question?
Sure.
I think yes, definitely, because we definitely can just like, once we like crawl the articles from the PubMed, right, we can like cross-check with the clinical trials database, and we can mark like which article is already in the clinical trials yet. So that's one of the way. But I think that's a simple solution for the question. Yes. Okay, so team 3, whichever one you all want to go first.
It's socket off. Sorry, I'm not gonna throw it. Question. When I'm talking, if you talk loud enough, can you walk around? Oh, okay. Never mind.
I'm sure they do something. HTML1, 2. But I also think
All right, hi. So we are part of Team 3. I'm Saket.
I am Agustin.
And our project is creating a question generation bot using Hugging Face and PyTorch. So again, all right, yeah. So in this presentation, we're basically going to take you, just give you a general overview of our product. Give you go a bit in depth into the architecture itself, show you a demo, and talk about future improvements. So to start off with the overview, right? So what are we trying to do here? We are essentially trying to create a program that, given any sort of text, it can generate questions out of that. You might ask why? Why is that relevant? Well, for a lot of students, especially in subjects like history and biology that are fact-based, it's been proven that quizzing yourself while learning the material is very helpful in retaining it for longer. So the purpose of this bot is essentially to help students, while they're like reading a chapter of their textbook, to just quickly generate questions to quiz themselves. And also, it can also be used by teachers to create mini interactive quizzes mid-class as well, just to make sure the students are engaged. And so here's like a really quick high-level overview of our model architecture. Essentially, what we're going to have is the input paragraph given into a model that summarizes that piece of text into the key information, because again, we don't want to make questions about any sentence. It should only be about the most relevant information in that paragraph. So we're going to summarize it, and then out of that summarized text, extract keywords. And using those keywords and the summarized text, we're going to pass it into another model, which actually generates questions, where the keywords are the answers, and the questions come from the sentence that answer might be within the summarized text.
Okay, so for the architecture, we decided to go with the T5 transformer, and for the data set, we decided to go with the Squad 2.0. Why did we decide this? So we actually wanted to build a mental health chatbot in the beginning, but we found it pretty hard to find a good enough data set to train our model in. So we decided to pivot, but not too much. We wanted to still focus on NLP and maybe chatbot, not sure yet. But so we asked ourselves, what makes a good chatbot, right? What makes a good conversation between people in general? And we thought that questions is a key component into having a good conversation. So if we can have our model generate good questions, then we can have a decent chatbot in the future. So I'll go more onto the data set. So the data set is Squad 2.0. It's from Stanford. It has over 100,000 questions and over 100,000 answers corresponding to those questions. The questions and answers are pretty broad. There's a very specific subject, which is what we wanted. We wanted to build a model that could ask questions given whatever subject we give it. Whatever context we want it, it can generate a question, right? There were also 50,000 unanswerable questions, but we extracted that. We didn't think it was necessary for what we were trying to go for. Yeah, so the network architecture. The network we used is a sequence-to-sequence model, right? A little bit of history. The first sequence-to-sequence model is actually an N model, which is the recurrent neural network. This model was mainly used for question answering chatbot and machine translation. So we were like, perfect, this is something we want, right? But there are two problems with the RNN model, right? Which I'll get into in a bit. But what is sequence-to-sequence model actually? It consists of two recurrent neural networks, an encoder and the encoder that processes the input, and the decoder that produces the output. The encoder and decoder can usually have the same or different set of parameters. So given an input text, it will learn to generate an output text. More specifically, in our case, if we automatically generate a question to that, it would ideally be suited to give the context and answer, right? So yeah, the reason we didn't go with the RNN model is because it has two downfalls. Vanishing gradient problem, which means that it would be difficult to capture long range dependencies or keep up with the context if it's too large. And inefficient parallelization, which means that it doesn't really make it doesn't have the best memory when it comes. So it really messes up the hardware if we give it too much. So we decided to go with the encoder-decoder model, which is transformer based. This allows us to stack the encoder and decoder are both stacks of residual attention blocks, which means that it does parallelization way better. And that means that the hardware will be way happier. And then, yeah.
So what we actually ended up finding was actually that there is this library of transformer models called Hugging Face, which is actually pre-trained for the natural language processing tasks like summarization, language translation, translation, etc. And so it also integrated nicely with PyTorch, which was our framework of choice. Again, really quick, like Augustine mentioned, the base T5 model for the summarizer, it has three parts: the encoder, the summary output, and the decoder. So the input that's given, it's converted into input IDs, which are then processed by the model to generate output IDs that are then basically translated from machine code to actual English. And speaking about keyword extraction, we didn't go with the model for this because we were actually able to find a really useful library which did this step pretty easily and efficiently for us. And finally, for the actual question generation bot, we again use a T5, a base pre-trained T5 model, but we fine-tuned it with the squad data set to make sure that it was giving us the questions in the format that we would like.
Yeah, so we had three ideas when it came to optimizing our data with our model, which was we wanted to drive our loss down, thereby improving our model accuracy, right? And we would do this with optimize, and also we wanted to be efficient, so we didn't want to do way too many experiments and update the hyperparameters. And we would do this all without overfitting our network. And with Optuna and PyTorch, we would do this, which one cool feature about Optuna is that it has pruning, which would allow us to halt any hyper tuning that didn't find the performance good enough. So that's what we wanted to do. Next slide. But we didn't have enough time to use it. We didn't have enough time to implement our optimization. The performance was decent. The good thing is that our validation loss was lower than our training loss, which means that it was training what it was supposed to do. And if we had enough time, we would use Optima into our model and implement weight decay so we could have better connections between the network.
So here's a quick demo of our model in action. So as you can see, it's a pretty basic front end at the moment. All you have is just direction text, and then you have an input box where you can upload your paragraph of choice. And so let's say you're learning biology, you're learning about the mitochondria, and you just want to make sure you're actually retaining what you're reading. Well, you can copy your paragraph of text from your textbook, enter it into the text field. And as soon as you click enter, under 30 seconds, it will return a number of questions. For example, what surrounds mitochondria? And the answer is the membrane system. Or what are acrostae? And those are folds. So again, just quizzing yourself while you're reading to make sure that you're actually remembering it. And it's just not going in one eye out the other. No.
So it's giving the answer also.
Oh yes, it's giving the answer.
So you're extracting the phrases or something and then turning it into a question along with the answer.
Yeah. So the keywords that we get, those are actually going to be the answers for the questions that are generated.
But see, the squad data set is quite diverse. Right? It's about general things. So I'm impressed that you're able to get that.
Yeah, actually, this one we
so
tried.
so this. Oh, sorry, same one. Oh, that's the same one.
In this demo, we get a paragraph or two from an article, and we go through it, and you'll see that it's not perfect yet. There's a question that says, what is the largest cryptocurrency in the world? I don't know what that means. It went a little too deep, honestly.
Right. Yeah, so there are still a couple of issues, like this one highlighted here, but it's also important to know that it doesn't work on just textbooks. It's also like articles or any sort of text that you want, really.
So what sort of accuracy did you get? I mean, if you have 5-6 questions, it generated with answers. How many were?
So actually, the way the questions are generated is that out of our summarized text, we get a certain number of keywords. And usually those keywords, like we found to be around 5 to 7 keywords for most pieces of text, for most paragraphs. And so the questions generated are for those keywords.
So how did you get word for cryptocurrency?
So the model realized that world is a keyword in that paragraph, and I think it can.
So then it extracted something about
that. So we'll actually talk about that in future improvements as well. Yeah, okay, yeah. So one of the key improvements we want to do is actually go from extracting keywords to key phrases. Because as we all know, a good answer to a question isn't just going to be one word most of the time. It's going to be a couple of words. And as you saw in the previous example, there might have been a larger phrase attached to world that could have been the right answer, or at least somewhat closer to the right answer, but that wasn't found because we were only doing keywords. So one of the future improvements of the model is going to be expanding that keyword definition. A couple other things is to actually train it on actual textbook text and those questions to make it more authentic and more human-like. And a couple other things we can do is just increase the size of the T5 model. Currently it has 220 million parameters, but we can bump that up to 1 billion, 3 billion, or 11 billion parameters, which will be more resource intensive, but also give us better results. And really quickly, so we also wanted to think past this this semester or this small project. So this is our go-to-market strategy, right? So what we're going to do is first have a proper website in phase 1 where students can upload any piece of text and not just get questions, but flashcards and quizzes that they can do and really have a proper website for. Phase 2, they can upload entire pages and maybe even chapters of textbooks, and we'll parse that and give them really good questions for that. Phase 3, they upload entire textbooks themselves, which will let us have an almost Chegg-style textbook database of questions for all sorts of textbooks. Finally, we get bought out by Chegg or Quizlet for $2.5 billion to disrupt the world, the billion-dollar industry that is education, and help a lot of students and our pockets.
And then you write a big check to AI Society.
Absolutely. We get our names on UTD.
Speaking of AI Society, I want to...
you use the pre-trained BERT, right? That's why maybe that's what helps it, right? So you did use BERT for the theory.
We did not use BERT.
We didn't use BERT.
No,
it was a different transformer.
It was just a T5 transformer.
Mm-hmm. It is still pre-trained, but...
On the squad.
Yeah. It was fine-tuned on squad.
So, but did you consider using, BERT along with maybe somehow?
Yeah.
Those pre-trained models help a lot.
So we did consider using BERT, but we actually found that for like natural language processing, at least what we're trying to do, Hugging Face actually had a lot of pre-trained models that were very almost state-of-the-art, very on par with BERT. So we ended up going with that. Also because there's a bit more documentation kind of related towards question answering. And actually, I think one thing we didn't mention was that our initial data set that we found was from Google, which had a lot of questions from Wikipedia articles and stuff and answers to those. But it was just a little too complex for us, and the context was too large. It was entire articles rather than like a couple sentences, which is what we were going for initially. So that's why. Yeah. Also, shout out to Rami, an excellent mentor. We would not have done nearly as much as we did without him.
Thank you guys. Good job.
Hi everyone, I'm Taya, and I know I just met you guys, but I think I feel safe sharing a little secret with you guys, okay? I'm 20 years old, and I still cry every single time I get a shot. Yeah, it's true, I am terrified of needles, which is a little counterintuitive because I have a tattoo, which is a little weird. But while doing research for my tattoo phase, I was looking and I fell in love with some of the styles that certain tattoo artists do that is so unique from other styles of art. But I was wondering, how can I enjoy their custom works without ever going under the needle again? And this rabbit hole sent me down until I found the solution, a neural style transfer. Today, we're going to be talking about some general definitions, the architecture I used to implement a neural style transfer, then we'll go over what I learned, some future implementations, and finally, we'll look at some cool art together. So first, some general definitions. What is a neural style transfer? Well, the goal is pretty simple. You have one image, which is the content image. That's the thing you want to keep in terms of content. So if I put an image of a cat, I want to see the cat at the end. The second image is the style image, which is the style you want to emulate. Think the swirly things from Van Gogh. The goal is to implement these two and together create one image with the content of the content and the style of the style. Pretty simple. Now, as an art history student, I can tell you that copying an artist's style isn't a new thing. It's been happening for centuries. The interesting part for machine learning is this neural word. So, how did we first begin? The first part of our architecture was using a convolutional neural network, which would process the two images in a feed-forward manner. The first thing you would do is, considering your content image, you would be able to go through and have this convolutional neural network. Each layer would pick up the arrangements and objects and output a feature map. Essentially, you want the high-level things that make the image the image. And this would give you a general overview and a lot of feature maps in different layers. If you're looking at the style representation, you don't really care about the arrangement of the objects because you're not trying to emulate that. All you want is the texture. The texture is going to be picked up by the convolutional neural network when you're given the style representation. So this image is a really good example. This comes from the 2016 study, A Neural Algorithm of Artistic Style, which is the initial paper that I read to implement this project. As you can see, when it takes the Van Gogh image, it doesn't pick up the cypress tree or anything in the background that actually makes the image itself. All it gets is its texture. Then in terms of the content image, it's really trying to see what is it that this is, which clearly it's picking up the buildings as the most important feature. Then it's going to input the two together, which I don't show here because this isn't one of the ones I utilized. So The convolutional neural network I used was a VGG19 model. This is a pre-trained model that has been trained on over 1 million images, and it can classify them into over 1,000 different categories. This is useful for a neural style transfer because essentially tattoos or images I could have put in could have been anything, and we needed to classify them before we could go ahead and create their feature maps and then do the overall output. Just some general information on the VGG19 model. It uses images of input size 224 by 224, kernels of 3 by 3 size with a stride of 1 pixel, max pooling of over 2 by 2 pixel windows with a stride of 2, and it uses ReLU. The paper details that using ReLU instead of the sigmoid function is much better for this style of classification, and it's also what we use for what I use for the later functions in this project. So as we said, the first thing we did was we extracted the features of the content and we got the textures of the style image in these layers. Now, what do we do with this? Now we have to compute the losses. So the feature map is based on nonlinear filter banks that are different, and they increase in complexity based on the position of the layer in the network. So like I said, VGG19 has 19 convolutional layers, and so each of those layers have a different amount of feature maps within them. So the way that you do this is you store in a matrix all of those feature maps, and then this is the loss function that you would use in order to take all of those feature maps and create one final representation of your image, also using the derivative of the loss here as well. You would use, this is a squared error loss between the 2 feature representations, and then you keep going over all of the feature representations. And through this way, you can find standard error backpropagation in order to get one final solid image. The same thing kind of happens for the style image, and then finally, you now have 2. What do you do with them? Well, you want to jointly minimize the distance using, so you have a white noise image, and then you use one layer of the content representation and multiple layers of the style representation. And you use this loss function, which the interesting thing about this loss function is that the content and style are very separated, and so are their weights, which means that you're able to change the weights of the style or content separately. And through that, you can really play with seeing how different you can create output in terms of how heavy, for example, the style is shown on your image. And for this, I also utilize the LBFGS optimizer, which is just an optimizer for the minimization function. Okay, so analysis. Why did I pick this structure? The alternative thing that I was studying for a big part of this project was general adversarial networks, or a GAN, which uses a different approach. It has a discriminator and a generator. The generator gives fake images, and the discriminator is trying to catch them and see if they're fake. Then you use a loss function to essentially improve the overall output over time. But playing with the 2, I ended up with this structure, again, because I really liked that you are able to create a difference in the weights and see the style loss change over time. So one improvement that I would do is that some of the results were quite abstract. I think initially what I was aiming for was to create a filter-like structure. So you would put in an image and you would get kind of the central part of the image as a transformation of the style. However, they did become more abstract than I had initially realized, and I actually quite love the results, so I'm okay with it. But I would potentially work on adjusting the scale of the trade-off between content and style. As you can see in these screenshots, they are a little small, but the style loss was much more stable over time, over iterations. This is 613 iterations, which took like an hour to run on my computer. And the style loss was very, very stable in comparison to the content loss, which starts at 0 and goes to over 800 million. So there is a lot to play with in terms of adjusting the scale on their trade-off. So some feature improvements. I think this would be really fun as a live action filter. Then you can turn yourself into art, or you could put tattoos on your body on a filter without having to go under a needle at all. Also, I think, again, trying to make this less abstract could be the way to go. So here's a general example of, this is a dog, and here is a feature map. This was the content image, and it's picking up the things that you would see are the main high-level features of this dog. So it's picking up its eyes, its ears, and there were 512 of these feature maps that were then put into the optimizer loss function. So this is the content. I wanted to see what would happen if I put the style of this crab tattoo, and the result is very interesting. I quite love this good boy. I think it's great that he still has some of his high-level features, his nose, his mouth. He's clearly a dog, but he's also quite more. This was me playing with the style weight. So the smaller style weight, even though the two images are very similar, you can see that the smaller style weight retains more of the content. So the dog's snout is more pronounced. You can see more of the gloss on its nose and its mouth if you're looking carefully. And more of its like fur streaks are showing. So it's clearly holding more of the content rather than the style, as opposed to the higher style weight image. This is my cat, Arya, from the Game of Thrones character name. And this is a Watercolor Lion. And this is something you would find after a very fun Friday night. So when I saw this image, I was a little concerned. I was thinking, okay, that thing on her hip looks very much like the lion's left eye. Is that a left? Whatever. It looks like an eye. And I was very confused. Why is it putting half of this lion's face on her hip? That's not what should be happening. But the more I looked into the image of the cat itself, I found that she actually has a very similar swirl in her fur that a feature map would pick up as something that looks like an eye. And to me, that was super cool because I would not have made the connection between a swirl like this and an eye or some shape like that. But the feature map did, and it's just impressive to see what high-level things are picked up that we wouldn't even notice with our own eyes or make connections. So something to play around with in the future. So thank you, everyone. I had a really fun time this semester. I had an awesome mentor. I had a great group. And I offended my parents by turning our cat into an eldritch horror. So it was a wonderful time. Thank you.
Good work. This is also very useful in data augmentation. One of the biggest problem in training convolutional neural network is there's not enough data available in a lot of cases, particularly in medical images. The data are limited. For example, I work in the area of mammograms. There are certain cancer data are very limited. But your technique can create a lot of data by augmenting, using data augmentation. Then you can use that to train the system. This is excellent.
Thank you.
Yeah. Are you graduating?
No, I'm a sophomore.
He wants to buy it. So if I take my house, picture of my house, and I give the style of say Van Gogh, then I will get my house as if it was painted.
Yes, absolutely. This works for anything. As you can see, this
You have an
toe
example
board.
of that?
Yeah, well, this toe board and this Monet picture are not like
So Monet
tattoo
picture,
based.
and what was the original picture?
The original picture was just a picture of one of our little toe boards from
Oh, okay, I see. Oh,
the things that deliver food and bring joy to all the
got it.
students. Yeah.
As painted by Monet, okay.
Mhm.
Nice, yeah.
Was that paper by any chance, one of in the collection of this guy who does these 2-minute papers website? I know he has something very similar to that.
There was a YouTube video basically.
There was a YouTube video, yeah. Well,
I
don't
didn't give
know
her.
if it's
I didn't give her the YouTube video.
the original paper is done by 3 German scientists in 2016, but there were a few YouTube videos implementing it in different things. Like
Yeah,
I was
I was
saying,
thinking of the paper itself. I think that's the one that I've read.
Yeah,
2-minute papers. That's on his, well, yeah, they're not 2-minute papers, but he talks about various papers
Oh.
on YouTube for 2 minutes. And this
It's-
was one that he highlighted.
Oh, that's interesting. I don't think I've seen that particular video, but I watched quite a lot of them.
Yeah, well, I've watched a lot of tattoo artists too, because I love tattoo art.
Me too.
But I feel sorry for any tattoo artists that would have to put one of these on their body.
Oh yeah, this is more for like just general enjoyment.
Wall, this is more like wall art.
Yeah.
So if you should, put up your tool on the web because, it will be a popular
Absolutely.
website where people can come and put the style picture and the picture and take the picture that they want. I would certainly do that.
Yeah.
Put my face as painted by Monet.
Oh, send me an email.
Or
I'll send you back an image.
We'll try that, yes, okay, cool.
Yeah.
Very cool.
Thank you. I think that is fine.
Okay, team 4.
So that's the last one, right? Last thing.
No.
Okay, next.
You can open too. I'll find out what that. Alright, so hello everyone. So my name's Kale. Oh, yeah. Hello. So my name's Kale.
Oh, I'm Richard.
Hi, this is Nasheen.
And we're here to talk about our movie plot generator. So take you through a problem. Imagine if you're a movie producer or something. You got a bunch of writers on staff, and they're going through some writer's block, struggling to come up with some ideas. What this AI does is it allows you to just fire all of your writers and just replace it with an AI because it's going to work. It'll be fine. Side note, I'm not like a business expert, so don't take me to court or anything. This is just my opinion. Replace it with the AI, it'll be fine. And so that's the current problem. And so this way, we will have 3 separate ways you can go about doing it. My way, which is a plan and write way, with it uses bi-directional Lstms to generate the story. Then we'll go to Richard's model, which will use GPT to help generate the story. And then finally, Nasheen's model, which will utilize Hugging Face transformers along with GPT. And then we'll talk about the future for this project. So for my plan and write model, I attempted to base it on the paper Plan and Write Towards Better Automatic Storytelling. And I split the data set, which is essentially a Wikipedia, I think it's about 34,000-ish movies off of Wikipedia and the plots for each of them. And I attempted to split it into like training and testing sets. And essentially what I did was that I split each plot into about 25 word sequences. And then I would feed 24 of them into the LSTM and have 1 word left I would try to predict. So that way it would go about learning the relationships between each word. And I used 2 bidirectional LSTMs. One of them will try to generate a storyline from the title. So you give it a title like The Virus or something like some, real impactful title. And then it will try to generate a sort of keyword storyline based on that title. And then from the storyline and the title, you feed it into another LSTM that will try to generate a story based on that. So I have a trailer right there that I can show it to you. So here we are. So I input Spider-Man as the title. It's running. And then soon it'll generate text right there, and it'll try and essentially create a plot around that title. Now, if you notice, it's a little incoherent and a bit rambly. I like to call it avant-garde. So I think it's, it's doing its thing. And then you put in a different title right there, the past and present. something deep, the viewer, and then it'll generate another sort of summary afterward, just as another example. So there's that. And so then, so going off of that, let's see. How do you like handle it? Okay. Awesome, there we go. Okay, so just to sort of go over what happened. Essentially, it's very simple to use and train, but as you saw, it's a bit incoherent than like the GPT model that we'll be discussing later. And that's mainly because it's not like a 100% like faithful adaptation of the paper, because due to time constraints and also just from a little bit of a lack of understanding. But I'm hoping that I'll get the knowledge from it and produce a better implementation of it in the future by adding an attention feature to the LSTM, which is what the paper did, and change the architecture of the model itself to help keep track of what it's already produced, so that way it won't ramble and talk about other things and introduce more characters when it's already have pre-established characters.
All right, so going forward, we're basically using GPT-2 for this next model. And so it's kind of like BERT, where it's trained on like millions and billions of tokens, right? And so I decided to just take only 4,000 of the Wikipedia articles and basically tokenize and categorize them, because like I didn't want to sit there and train the model for 34,000. And so basically I was kind of confused on this at first, because I was like, is transfer learning really just taking somebody else's like model and like cheating basically? But yeah, that's basically what I did. And so if you can see the meme, that's GPT-3 that's coming out, right? And so yeah. And then the generation here, yeah, so these are the tokens that we tokenized, or the articles that we tokenized, and we labeled them. And then we go through here, we can see the stories that it ends up generating, and it says, oops. You can see on the first stories, it goes through a horror sequence, and so it's very coherent. Like for example, on this third sentence here, suddenly a man in a red convertible with a rifle in his hand drives up to them, and he fires at them, blowing up the car. And yeah, so we trained it for longer, and it ended up. Oops, I keep doing that. We trained it for longer, and it ended up producing the categories as well. I keep doing that. And so I was thinking that I separate the categories, which is what Nashin ended up doing. So I'll go ahead and yeah. So it was fairly accurate, fairly coherent, but it was slow and needed a lot of data. And so yeah, I discussed that I needed to separate the categories, which is what Nashin ends up doing.
So I think my team has already gave you the idea of what the problem statement was and how did we get the data set from. So I ended up doing this using the GPT-2 pre-trained model, and then fine-tuning it with my own data. That's the data that's gone from the Kaggle, and using the Hugging Face model transformers library. So initially we went about like dividing the data into training and evaluation data, and then try to define our model arguments and our data training arguments, and then trying to train it, and using the different configs that are already available from the library, and then providing the genre and the text. So we basically give the start of the statement, and then the end of the statement. That's how the data was formatted, and that's where we try to give the genre and then the text. So I'll just give you a quick example of how the model performed. So this is an example. Yeah. So here I've given superhero as Spider-Man, and then this was the text that was generated. I'll play this text at the end of the video, but yeah, this is how the text was generated, and it was fairly, it seemed good to me. Yeah, that's how I tested it. So yeah, that is one of the example, and I try to give the another there were different the special tokens that considered here were genres were having horror, action, superhero, and all of those, drama. So anything we give, and then the data, the plot was generated accordingly. Yeah. So these are the two examples.
These plots were already existing or anything new?
So we did get plots from the Kaggle data set, and then we tried to fine tune the GPT-2 model by giving that data set, and then try to regenerate, giving our own text and try to get the movie plots. So review, what went good was that the most of the heavy lifting was done by the libraries, and as Richard mentioned, that it was taking a lot of time to train the data, and the next improvement would be going ahead with GPT-3, where I think we can go, rather than generating just an a small plot or something, trying to get an essay, or how the other team did it, like a question answer. I think something that can be done. So moving forward, what can be the improvements for all the models that three of us came up with was that we want to update this to GPT-3, where we're using GPT-2, and then try to have the responsiveness or the results coming out more creative. We aren't sure how to get that right now, but yeah, that's what we want to achieve. And also have a web application or a mobile application, and have this model as a service that would directly take up the input and then get back the plots that we would need, and also have people rate our generated stories to understand how we are doing and how basically evaluate our own model. So these are the references that we used, three of us. What are the papers that we used, and and also have our whole code checked in on GitHub. So those are our links, and I just play out. I don't know if this will work, but yeah.
Alan Tudyk is sent on a daring mission to stop a deadly robot that has attacked Thailand in the hope of saving innocent people from destruction. After failing numerous tests and making several failed attempts at weapons use against an approaching robot war machine during World War II by its own creators, he finds himself back in space with friends Bill James and Johnny.
So this was being given.
What is the, sorry.
So this was using the. So this was basically using the genre as a superhero, and the statement just a Spider-Man. Spider-Man was given, and then that was what was generated by the model. Yeah.
So your input was Spider-Man and the genre.
Yes.
That's it. And
that's
then
it.
all the information, whatever comes from learn. Okay.
Yeah.
Awesome.
And I think we would like to thank the entire society for artificial intelligence society to actually giving us this kickstart. I'm doing this for the first time, and I think most my teammates as well doing it the first time. And I think we really got a really cool mentor, Vignesh. I don't know. So yeah. So I think that was really great. Yeah. Thank you so much.
Again, what I want to find out is that did you get a plot that is not the input to the system? Or you just pick the plot and gave you, from the list of plots that you're trained with?
So what Dr. Tamil is saying is that, is it the case that you can just pick some random plot and give it to you and just adapt it slightly? Maybe, find a plot about, similar to Spider-Man, just replace, Batman with Spider-Man and give that to you.
Mm-hmm.
Or is it that it's giving a brand new plot that is merger of, stuff learned from various plots that you fed to
branding, right? That plot.
Yeah, the one that was
exactly.
Yeah, the one generated was a new one. And also what I observed was when we were trying to run multiple times giving the same input, I was getting a different output. It was not always the same. So yeah.
Because in the past, people were trying to write a new research article and based on all the article that has been generated, and it was not successful. So
I think those that have been written papers have been accepted into major journals.
that is different. Anything they will
Because I got this is much simpler. It's just one paragraph, right? Yeah.
Well, we didn't do like much research into like if our models are like or like the stuff that it's spitting out, we don't know if like it's being repeated, and we don't know if like we don't know how good our
Yeah, this was like this. Like, what is the performance criteria? Like,
yeah, exactly. So like what we were thinking was that like we on the very last bullet we have people like rate our generated stories so we could see, oh, like it's just literally repeating that Wikipedia article and it's terrible. You know, so yeah.
Yeah, people have to do that.
Exactly.
so
But I mean, you could keep generating until you find something there.
Yeah, exactly.
Sorry, go ahead.
It's on your second GPT model, right? You're using Wikipedia articles, and then you switch to a Kaggle data set. Is that
No, it's the same data set except for the middle one. I basically shrank it down because like I used the whole Wikipedia article and I put it into the model.
Okay.
So like it would spit out like the whole article basically for mine.
And then another thing would be, does GPT automatically insert randomness? Like if I put Spider-Man as input 3 times, would I get the exact same output 3 times? Or like what, for the RNN model, right? I was wondering if you would like feed in a random number along with it, so that way it would possibly generate more like random sentences. So like I don't know if GPT handles that. I forgot, but
I thought she already said that, right? If you feed Spider-Man.
Exactly.
you'll
It was
get
not the same
each time you
response
get-
that that was. Yeah.
There's a well-known episode of South Park where Cartman gets kidnapped by some Hollywood producers and they won't let him loose until he invents a bunch of new movie plots. I think you would enjoy watching that after the project.
All right.
Sorry about going a bit over time, but team 5.
That's 2, 4, 5, 6, 7. The 17.
I thought we were told to be 60. That's why okay. Can be more than 6.
So is this the last? One more team after. So there are 8 teams. 6.
Well, there's 6, but some of them had differences, so but 8 total.
Okay. So
Like one this group is like one group, right? You guys have one group to different. My gosh. Okay, I was like two teams.
oh, okay. So one group. Okay. All right. Okay. All right. Let's just do that. Okay. Fast then. Yeah.
Hi, everyone. I'm Shreya,
I'm Ryan. And I'm Ben.
and we are Group 5 with the project Hands Up. So, what is our project? Well, it is an object detection program that identifies and locates a raised hand in a live video footage. What was our motivation behind choosing this project? As we all know, the COVID-19 pandemic has caused an increase in the use of a virtual classroom. Although there is already a raise hand feature on virtual meeting platforms like Microsoft Teams and Zoom, we wanted to explore the object detection aspect of ML and combine it with the relevant topic. Additionally, object detection has multiple real-world applications, so we wanted to delve into a little deeper and work with a project that utilized this aspect of ML. What method did we use? Well, we used something called transfer learning, in which you utilize a pre-trained model through which you send your own data and retrain it to give you the output that suits your needs. We made use of a CNN architecture, which is mostly used with images since it involves layers and filters. And looking at these 3 images at the bottom, you can see a visual of how transfer learning works So in the image on the left, in traditional machine learning, essentially you give it a data set and it creates a custom model for that data set, and you can only use similar data sets to give it the output that you want. But with transfer learning, it uses the knowledge it has learned from the first two data sets and applies that and retrains the model based on the new data set you give it, and then produces a new aspect or a new output. With the middle image, you can see that there's a certain layer. There's certain layers that are fixed, which is the learning part of it, and then this is the retraining part of it, which is a new data set that you give it. And then basically each convolution layer is where it max pools everything and then gives you a number for a pixel. So how did we approach this project? Well, our team used a tutorial we found off YouTube, which detected whether the individual within the video footage was wearing a mask or not. We have linked the video in our last slide. Since we followed the tutorial, the only major thing that changed was the data set that we sent in which our case was a variation of raised hands. We utilized a custom data set of 128 total images where we split them between 110 training images and then 18 test images. And as you can see, each of us sent in our own images with different angles and variations. Once we had the data set, we downloaded and used label image, a pre-written program in Python, to draw a bounding box around each of the 110 test images that we wanted to send in. And that bounding box created a separate XML file with just a hand inside of it. Next, we sent these XML files to a pre-trained model, which uses the TensorFlow object detection API and retrains it to detect the hand. This process uses an SSD, which is a CNN network that learns to predict bounding box locations and classify the location of these boxes. These two processes, the predicting the bounding box is called localization, and then the classifying the location is known as classification. So in detail, localization is essentially the process of taking different X and Y values for the width and height and drawing bounding boxes based on these coordinates so that it can learn. And then classification is where it identifies the object based on what it has learned. The last step we took in was to send the 18 test images through the model to see how well a model could identify the hand. Now Ryan will dive into how our model performed.
Okay, there should be a video appearing right here. There it is. Oops. So as you saw in the video, it seemed to perform pretty well at recognizing and drawing the box around both of my hands. However, at the end, the boxes became a little inaccurate. And what you have not seen is that there are many cases where our model has classified things that are not hands as a hand. In the bottom image here, that's my ceiling fan, which it has created two green boxes around because it thinks the ceiling fan is some hands. And so we believe that our model has been overfit to our data set because we only have a small data set. We only created a little over 100 images to train and validate our model on. And we had a total of 200 epochs. So we iterated through our small data set 200 times to train the model. And there are a few ways for us to prevent this overfitting, which would be to gather more images that have a variety of backgrounds behind the hand, different lighting in each photo, different skin color, outfits, and many different other objects in the photo too. And there are also other pre-trained models that we can choose from and try out to see which one might be the best for this situation.
the TensorFlow object detection API provided a list of different pre-trained models for us to choose from. And we chose SSD, the single shot multi-box detector for this, but we have yet to try the other ones.
Here is a good place where you can use neural style transfer to augment your data set. So you were saying that you want different backgrounds, different colors, all those things, right? So that you can do because your set is 110. And what is the backbone of this?
The backbone?
Yeah. You used the transfer learning.
Yes.
So that you transferred on a backbone, right? What is that one?
Well, what we did was we used a like YouTube videos. Essentially, what we did was we just gave it a new data set, but it was like a tutorial video essentially. So whatever instructions were like in the video, essentially, we just followed that. But
you used a network like a efficient data or something. You used a network.
Yeah.
And what is that network? And it had a backbone like a ImageNet or something is there.
It was ImageNet. The pre-trained model, yeah, the pre-trained model used ImageNet, where I think it was over like around 1 million videos or photos that it trained it on, and then we retrained it using our own like hand data.
All right.
Okay, so for future improvements, we want to be able to make our program be able to actually recognize hands better. So like Ryan said, it recognizes ceiling fan as a hand. And I'm not sure if you saw, but also in the demo, there's like this one frame where it recognizes Blazer as his hand.
Yeah.
So we want to be able to improve on that. And also, we thought of this problem where sometimes people will be doing some random things on camera, like let's say for example, like they're stretching, right? So our program might be able to recognize that as them actually raising their hand, but when in reality they're just stretching. So we want to prevent it from recognizing that as raising their hands. So one way we could tackle this is to put like a timer on it or something. So if their hands are in frame for like, I guess 5 seconds, then they're actually raising their hand, right? And we also could build off of our project and have it recognize hand symbols. So it could recognize like a whoosh or a thumbs up. And building off of that, we could also make it recognize ASL. So we can also make words off of hand symbols from that. So here are our resources.
The first link is a video that we based it off of.
And thank you.
Well, this is a good example of an overfit. So you have to look and see how you can overcome this. You can also decrease the complexity of the network. That's one way to do it. The second way is you have to do data augmentation, either using GAN or the neural transfer. You have to create, thousands of these hands.
And by augmentation, that would be such as rotating or cropping.
Yeah. There are multiple things you can do. That way, you will be able to, overcome this overfitting. And also, there are other techniques, dropout, and a lot of things you can also do in addition to that. So this is a good, you can learn now how to overcome this. That would be very valuable.
Thank you.
Excellent.
Okay, last but not least, team 6. team session.
All right, so I'm sure at some point in your life, you've had to go onto a website and verify that you're not a robot, because apparently we can't get computers to tell the difference between a machine and a human. So society invented stuff like this to tell the difference. And what we did for our project is we created a robot to fool the system and crack the Captcha. So what was the overview? Well, what was the motivation for our project? So originally during the learning phase of AIM, they gave an example of finding a basketball in the wild. And so we figured it would be kind of funny to try to make a project to do that, except as you can imagine, there aren't very many data sets for finding a basketball in the wild. So then we moved on to maybe trying to find the bicycles in an image, but we couldn't find a data set on that either. So we settled on Captcha for text, as you can see here, 2B827, things like that. And with these images, we wanted to predict what the text is. That way we can use that information for a variety of different things in the future. For our project, we used a Kaggle data set of about 1,000 images, splitting it between training and validation data sets. To do this, to predict the different images, we used a convolutional neural network architecture to extract both high-level and low-level features. And for implementation, Keras and Tensorflow were our choices because of the wide support in the AI community for those. And as you can see in the image, break the image into parts, look at the parts, and then look at the parts like together to get the more high-level things.
Okay, so our data set consisted of over 1,000 of these Captcha images, and we needed to pre-process all of these different images. There's a couple of different things that we need to keep in mind when we're pre-processing these images. The first thing we need to do is we need to scale the images, and then we need to resize these actual images in order to be able to be input into our actual model. So another issue when we are actually comparing our Captcha images is we have a string, which is the actual value of the Captcha image, the thing that we actually want to predict. But what we have are images. So we have to create some sort of mapping between the actual string and the output of our network, which is generally some sort of tensor. So the way we did this is we have a one-hot encoding for the actual strings, which is our forward mapping into a tensor. And then we also have an inverse mapping, which takes the output of the network and maps it back down into a actual sequence of characters that would actually be able to be passed to the Captcha test.
All right, so when we developed our models, we used some documentation on the internet, because this is our first time doing this, using like tutorials to sort of figure out what we were doing initially, and then we expanded a little bit upon it. When we did this, we had two different models, and then we eventually chose one of them to move forward with. That way, if like the robot in the picture, we can successfully rather than unsuccessfully detect images like that.
Okay, so the first model is basically the architecture is described as a convolutional recurrent neural network. And basically what we do is we try to pass first the image into these convolutional layers in order to extract a meaningful feature map. And then we take those feature maps and then we're able to pass them into the recurrent neural network, or a deep bidirectional recurrent neural network, in order to further extract our predictions. The reason that we use the recurrent neural network here is because its ability to actually maintain context of the previous words or whatever that's in the actual word. The reason for this is because we're actually doing sequence prediction on these Captcha images, because we want to predict the entire sequence of those characters. The actual transcription layer is used through, we use various different transcription layers depending on which model we use. But in this case, we use CTC loss, which basically takes our image or some sort of feature map, and we split these things into our time series, and then we create a path in order to predict on which of these like various letters that the actual box belongs to. So it can also be a blank box, so it can also predict for it to not actually have a character associated with it. And then the sum of the probabilities across all of these, across the entire function would of course be 1, because we have some set of like conditional probabilities that we're summing across. So this would be the actual transcription layer for the CTC model. There's also another transcription layer where we take the output of the model and then map that into, as I said before, map that into an actual sequence of characters. So we take the output of the actual convolutional network and then map that to a sequence of characters.
All right, so after working on the first model for a while, we moved on to the second model that we made. And it uses convolutional layers to extract broad features. And it breaks the image basically in 5 parts, just as the other one did, and predicts each section. So it's a functional model, uses categorical cross-entropy, which is useful for categorical data like the ones we are using since each letter is one of the categories. And essentially how the model works, well, firstly, we trained it for 30 epochs with the Atom Optimizer. And essentially how the model works is there's multiple convolutional layers, which is to extract broad features, as well as max pooling layers, which is to reduce the dimensionality of the data. And eventually it is batch normalized so that recenters the data, renormalizes it, and then it is passed into 5 different sections, 1 for each letter. And so each one, there's a dropout layer to reduce overfitting, and then finally its guess for each letter is output. So our accuracy was about 98%, and that's for one of the dense layers at the end, one of the letters. And so our loss function is given here. And so you can see further how it works in the demo.
Can you skip the slide?
Okay, well, anyway, before the demo, so some problems we had in our learning was overfitting and narrow scope. So overfitting, as I'm sure a lot of you know, kind of like the graph shows here, when it essentially memorizes the data set and picks up on every little element rather than on trends or patterns. And that could have been a little bit of a problem in ours, because as soon as we tested it on a slightly different style of Captcha, like on screen, you can see those have 6 characters instead of 5. And with our CTC breaking it down into like a certain number of boxes, it just didn't work out with that same formatting. And I'll leave it to Jack to explain which model we chose.
So ultimately we chose our second model as our best model, mainly just due to time constraints and implementation restraints. We weren't able to get the other model to the best accuracy, and the second model had a reasonable accuracy and was working well, so we chose that one.
Now for the demo.
Okay, so now we have a live demo. Hopefully nothing breaks. Okay, so the first application here was developed by Jack and is deployed on Heroku. And basically what it does is we take an image and then we feed it to our backend, which basically takes our model and runs the model on the actual image. And our model then predicts what the image actually says. So like, let's pick an image here. For example, this image says 3x5fm. So we can pick this image and then upload it. And we can see that our model correctly predicted the sequence. We can do this for different images as well. So this one says 4C FW8. And as we can see, our model once again correctly predicted the sequence. And now for our other demo. So for our other demo, the main goal of Captcha is the completely automated Turing test in order to tell humans and computers apart. And the point of this is basically so that we can prevent bots from accessing different websites or different applications that we don't really want them to access. So with our model, I wrote a little web application here, which is a very simple Captcha test where if we input an incorrect guess, it'll reload. We're not going to be able to get to the next page. But if I actually input the correct guess here, we're going to be able to get to the next screen. So it would be really unfortunate if someone wrote a bot to just bypass this. So as you can see, we instantly bypassed the Captcha test. And that is using our model. So this is an example of a real-world application of our actual model, and also an example of a real-world application of some sort of program like this, where you would have a bot and it would just bypass these Captcha tests, and we'd be able to get into websites where we're not really supposed to be able to get into as a bot.
All right, so what we could do with this in the future is we could train it for different styles of Captcha, kind of like the one on the screen there, because as I said, our data set was limited, only about 1,000 images, and they were all relatively like the same style. And so in the real world, as you can see with those stop signs, they're completely different. You never know what you can expect. And so what you can do with an improved Captcha is create future versions of the test based on that Captcha so that in the future people don't get into websites with the same models. Otherwise, there wouldn't really be any point, right? And then to further develop the Captcha algorithm, something we can do is rather than like what we did with the limited time we had, which is break it up into like a finite number of boxes, we could create object bounding boxes that characterizes the exact location of each character. And then with like stuff with the stop signs, we can extend the whole algorithm of general like optical character recognition instead of just Captcha. And that could be used with things like self-driving cars or like VR or something like that. And that could have a really good impact on society. And this is our source code and our references that we use to help us make it. And that's our presentation.
Can you use the same thing for handwriting recognition?
Handwriting recognition? Yeah. A similar approach you could use for handwriting recognition.
Yeah, I was going to ask a similar question. Have you compared what you have done with the state of the art in the Postal Service, recognizing zip codes, which has been one of their key challenges for a couple of decades? Did you look into that at all?
No, we have not really looked into that.
Right, we just took our very limited data set, split it in between training and validation, tested it on the training, and then, well, not tested, trained it on the training, and then tested it on the validation. And so it wasn't the exact same data, but like I said, it was very similar, and that's probably why we have very high accuracy, because it's the same style.
Yeah.
And kind of like with this one, it looks like almost the exact same style, but it's a little bit different. And even with that, it was relatively unsuccessful. And like just in future development, just using a more broad, a more diverse range of data and a more deep
Yeah, that makes
algorithm,
total
I guess.
sense. I was just curious where the postal system where their technology stood today with regards,
Right.
to these fast envelope passing machines that
Yeah.
scan for the zip code and route it to appropriate destinations. I was just curious, but if you don't know.
Yeah, we don't know. It sounds really interesting though. So.
The issue I think with your first model is the sequencing part. Like you don't need the context from your surrounding letters. So
Yeah.
you did object recognition on the second model and it clearly performed much better.
Yeah.
So I feel like the fact you had like this, you had the recurrent part of it because you're trying to incorporate prior letters. That's probably what was tripping it up.
Yeah.
Other than that, yeah, it's good.
Any more questions?
Okay, so we're just gonna wrap up real quick. So we have a couple of shout outs. So our mentors this semester was Eric, and he just had to leave, so he's been a bit ill. So sending good thoughts. We had Vicky over there, and we have Rami over there. And Gokul. And then thank you to the AI Society marketing and executive team for having planned out tonight. So thank you guys. And thank you to the faculty especially and everybody else for coming out tonight. I really appreciate it. Thank you. And then lastly, if you need to I guess register your membership attendance. If you go to this link, this is the code. Yeah. We don't have that. That's so good. All right.
That's good. So the judges don't have to do anything else, right?
Everybody come.
Okay, everybody.
Thank you so much for staying.